Welcome to Elementary Calculus, Chapter 3, Section 3, where we will be talking about rates of change. These notes were created sampling some materials from Calculus with Applications by Greenwell, published by Pearson. And in our conversation about rates of change, you're going to see some familiar elements. The average rate of change is described using the difference quotient, which is directly related to the formula that we have used to calculate the slope of a line between 2 points. And what you're seeing in this shaded box is essentially y2 minus y1 over x2 minus x1, which is change in y divided by change in x, which of course is slope. And just in the way of practice, let's do one of these problems, because then we're going to adjust it a little bit when we start really applying it to the difference quotient and bringing limits into the mix. So the average rate of change for this first function between x values of 3 and 6 can be calculated by first finding f of 6 or f of 3, but I'm going to do f of 6 first. So we have 6 squared plus 6, which is 36 plus 6, which is 42. And f of 3, we will need that also. 3 squared plus 3, 9 plus 3 is 12. And we'll need 6 minus 3, which is 3. So now we can take f of 6 minus f of 3 over 6 minus 3. We can fill in these blanks, sort of. We have 42 minus 12, all divided by 3, which is 30 divided by 3 with my terrible handwriting, which is equal to 10. So the average rate of change between those two x values for this function is 10. Now, x squared plus x, I didn't use my graphing calculator in advance to see exactly what this looks like, but it should be fairly parabolic, and at an x value of 3, if we're here, and at an x value of 6, we're here on the curve. Do I have a straight edge anywhere in here? Not so much. I just prefer to draw straight lines because in this particular case, I really want to highlight the fact that if we draw a line, can I draw this line? The line that passes through those 2 points, you'll see, is sort of staying on the high side of the curve. So again, the average rate of change is talking about an average rate of increase, and all we have to do is find the slope of the line that passes through the beginning and ending point, and we sort of disregard what's happening between there. And we can go through that same process for this next problem, but I think you know how to plug numbers in and do subtraction and then reduce a fraction. Then we move into instantaneous rate of change, which is the somewhat more interesting topic of conversation here. And the instantaneous rate of change is what's happening, or the rate of change at a specific moment. So we're not looking at 2 points on a curve as much as we're really trying to hone in and look at specifically 1 point on the curve. And if I come back up to this previous beautiful graph that I drew, you can see even, and this would be the, let's see if I can pull this off. It is possible. So if between 3 and 6 in this particular example, the average rate of change is 10, there should be a point on the curve somewhere between 3 and 6 where the instantaneous rate of change is also 10. And I'd be willing to bet that it's at maybe, if I can get my pen to work, I'm trying to be too creative here, maybe I'm pushing it a little. Maybe it's at this point right here, and if I try to draw a line that's parallel to the previous line that I drew, let's see, that's pretty close. That second line that I drew is more like a tangent line, and in fact it is. And it would be nice, it would be valuable to someone if we could figure out when, or for which x value, the slope of the tangent line is the same as the slope of that secant line. In other words, it would be advantageous sometimes to know when the instantaneous rate of change is equivalent to the average rate of change. And so let's come back into the particulars of determining average rate of change. So we're using the difference quotient here, which is in the middle of your screen, and that involves a function. So we're going to be given a function in example number 2 that we can work with. And in order to calculate the instantaneous rate of change, we're going to use the difference quotient, and we're going to take the limit as h approaches 0 for the difference quotient. And what that does is, as this h value gets really close to 0, the input into this function as compared to this input into the function, those two values are going to get really close together. They're going to be super similar. So if this is 3, for example, and our h value is only 0.000001, then the first part of the difference quotient would end up being 3.0001. So the x-coordinate here and the x-coordinate here are really similar. And if we were looking at some kind of a curve, what that does is 1, 2, 3, it puts our first point here, and our second point is almost right on top of it. They're really close to each other. And so if we can find the slope of the line that passes through those 2 points, this is looking a lot more like a tangent line. And if we can get those 2 points to be, in a way, infinitely close to each other by taking the limit as h goes to 0, infinitely close together so that the difference between their x-coordinates is almost 0, then we will end up with an actual instantaneous rate of change. So let's apply that in example number 2. We have our function here, and we're going to be looking for the instantaneous rate of change when x is equal to -1. So this is going to be our a value. But first, let's just calculate the difference quotient. So we have f of a plus h. Well, let's make the a into a -1. Let's just do it right away. Do I want to do it that way? Let's do it with a plus h. Sorry, I'm being indecisive. A plus h, given this function right here, that is equal to a plus h, quantity squared, plus 9 times a plus h. And let's expand this and combine any like terms that we can. If I FOIL and combine like terms here, I get a squared plus 2ah plus h squared. And then the second term, this term right here becomes plus 9a plus 9h. And we already know from the difference quotient, if you look at the top of your screen, we know what f of a is. That's going to be easy. F of a will equal a squared plus 9a based on our function, and h is h. So let's take f of a plus h and f of a and put them into the format for the difference quotient. And let's put the limit in front of it as long as we're at it. So we've got the limit as h approaches 0, and our difference quotient is a fraction. The numerator says f of a plus h first, which we just expanded and determined is a squared plus 2ah plus h squared plus 9a plus 9h. And then we have to subtract the entirety of f of a, which is a squared plus 9a. all divided by h. So the next thing I'm going to do is come into here and distribute my minus sign, and then we will combine like terms. So I'm going to continue writing the limit. We always want to bring that with us. In my numerator, a squared plus 2ah. I won't read it out loud. You can just write it down. Make sure you distribute that minus sign to both of the terms in the parentheses up there. Still all divided by h. And then we notice, of course, that the minus a squared and the positive a squared are going to cancel each other out. The minus 9a at the end and the positive 9a in the middle are going to cancel each other out. And once those two terms are gone, we're going to be able to do some reducing with the remaining three terms that are in the numerator. In an effort to save some space, let's go ahead and do that now. I'm going to cancel out this h, which means, and I have to distribute my division. Please don't forget that. In this term, this h is going to cancel. In this term right here, only one of those h's is going to cancel, so I'm going to cross out the exponent so that we only have h to the first power remaining. And this next term, the plus 9h, that h will cancel. And let's write down what we have left. Still the limit. As h goes to 0, it's not a fraction anymore, so I think I'll put my square brackets here to make sure it all stays bundled together. We still have the 2a, and we have plus an h, and plus 9. And now, if we take our limit and actually apply it to this expression, we can do that using direct substitution here, which is very nice. We don't have any division or anything that we have to watch out for. Essentially, this is a polynomial, so we can just plug that h value of 0 in. And honestly, let's put an equal sign here and here, because these three statements are equal to each other, and then I'm going to put another equal sign down here because this is equivalent to all of those, and now all we have is the 2a and the plus 9 because h went to 0, so that term zeroed out. Now, since we know that we're trying to find the instantaneous rate of change when x is equal to -1, that's our a value, so I'll write a little note here that says that a is equal to x, which is equal to -1. We'll plug in that -1 for a, so we have 2 times -1 plus 9. That's -2 plus 9, which is 7. So our instantaneous rate of change for this function at that particular x value is 7. This is a process that you're going to want to practice, especially if it ends up being a free response question on a test, or if you're going into Calc 2, you will definitely need to demonstrate your ability to perform this process. Let's see. So here we're given a different function, and this function is called s of t. The name of the function is s, our independent variable is t, and that's not a big surprise. Usually, lowercase s is used to represent a position function, and t represents time. So this is very likely what's happening here, and we'll see functions called s again in the not too distant future. And let's find the instantaneous rate of change. The first thing we need to do is figure out s of, just like we did up here, in the, oh, it's behind me. There it is. This time it's going to be s of a plus h. Too many colors. It was turning into Christmas there. S of a plus h. For this function, ooh, this is going to be a little lengthy. You might want to write a little smaller here. We've got 3 times a plus h, quantity squared plus 5 times the a plus h minus 7, and I'll try to keep working vertically here. Let me move over to the left a little bit because this thing's going to get not out of control, but it is going to get lengthy. We've got 3 times a squared plus 2ah plus h squared close plus 5a plus 5h minus 7. Then let's distribute the 3. All right, that is s of a plus h. We also need s of a. That's the second half of the numerator in the difference quotient. All we're doing is replacing the t's with a's. Oop, I said t, so I wrote t. That was supposed to be an a. So 3a squared plus 5a minus 7. And then we've got the h that's in the denominator of the difference quotient. So we've got everything that we need. Let's write down our limit as h goes to 0. And we've got our gigantic fraction. And it's going to be maybe out to here. All right, let's write it in. S of a plus h expanded. 3a squared plus 6ah plus 3h squared plus the 5a plus 5h minus 7 minus, now I'm going to do a, I don't want to do that. I was going to do a little shortcut, but minus s of a, which is 3a squared plus 5a minus 7. And we will, of course, need to distribute this minus sign and switch the sign on all of those terms. Don't forget your denominator of h. All right, now here let's do one shortcut. Just to compress the process a little bit, let's cancel out the 3 terms that we're seeing down here with the 3 opposite terms in the earlier part of that numerator. So we're subtracting a 3a squared. That's going to cancel out this positive 3a squared. We're subtracting a 5a, a positive 5a. So we're subtracting a positive 5a, so this positive 5a is going to go. And we're subtracting a negative 7, which is the same as adding 7, of course. So that plus 7 is going to cancel out with this minus 7. So that term will go, and this term will go. When you're using the difference quotient, remember that all of the terms in f of a or s of a, whatever it is, all 3 of those terms, or however many terms there are, should cancel out with earlier terms in the numerator. And in this case, they did, so I know that I'm on the right track. And should we cancel out some h's also? If you're comfortable canceling out some h's right now, let's do that. Otherwise, if you'd like to rewrite this statement that we have already, keeping this term and this term and this term, that's fine. And the denominator of h, all of those things are still there. If you want to rewrite this line, please do. Because I'm a little short on space, I'm going to go ahead right now and I'm going to cancel out this h from the denominator with this h from this term, 1 multiple of h from this term, and the h from this term. And now I'm going to write down what remains. We still have the limit, so this is equal to the previous line. The limit as h goes to 0. We don't have a fraction anymore, so I'll use my square brackets. We still have a 6a. We still have plus a 3h. And we have a plus 5. When we apply the limit, it's going to zero out this middle term, so that'll disappear. Now we have 6a plus 5. And our problem told us that we're finding the instantaneous rate of change at t equals -2. That's our a value. So let's plug that in. A equals -2. So we have 6 times -2 plus 5. -12 plus 5 is equal to -7, which means that it's just a coincidence, by the way, that this is -7 and that our previous instantaneous rate of change was +7. Total coincidence. Different function, different x value or t value, and the instantaneous rate of change for that function at time or t equals -2 is -7. That would be the slope of the tangent line to this function at the point where t is equal to -2. When we talk about speed, functions that involve speed, which is very common, we'll talk about instantaneous rate of change, and speed is usually considered to be positive, but every once in a while you'll calculate a speed as an instantaneous rate of change, and you'll get a negative value, and that negative is going to indicate direction. So a positive speed would keep you moving forward, or maybe in the upward direction, and a negative speed can be considered moving backwards, or sometimes in the downward direction. So instead of saying speed, often we'll refer to it as velocity, because that includes direction. Velocity is considered to be the instantaneous rate of change of a function that gives position in terms of time. And very shortly we're going to introduce the word derivative, and we'll find that velocity, or a velocity equation, is the derivative of a position equation. Suppose that the position of an object moving in a straight line is given by this function. Find the instantaneous velocity. And again, finding the instantaneous velocity would be the same thing as finding the instantaneous rate of change for that function at that t value. I'm not going to go through those motions because it's the same process as we saw in the previous two examples, and I'm going to pause for a moment and be right back. Alright, after a quick pause, let's move into this, I think this last little subsection. Yep, we're on the last page where we're talking about marginal cost, revenue, and profit applications. So we're getting into some word problems now, and you should read through this. This is good information, but the thing that I wanted to, or the couple of things that I really wanted to point out were what I have already highlighted here for you, and that's that marginal cost is essentially synonymous with the instantaneous rate of change of the cost function. And when we talk about revenue, that same idea will apply to the relationship between revenue and profit. So in this example, if the total profit in hundreds of dollars from selling X items is given by this profit function, and we want to find the marginal profit, then we'll need to find essentially the instantaneous rate of change of the profit function, and that will give us the marginal profit. And then we'll use an x value or an a value of 3 in order to find that marginal profit. And I'm happy to go through the motions one more time in applying the limit to the difference quotient, and then we will have wrapped up this section. So let's see if we can knock it out. All right, p of x is our profit function. I'm going to use p of a plus h just to highlight. Still using the a plus h even though the name of the function has changed, and then we'll figure out p of a. So if you want to be working ahead of me on this problem and then comparing your work to my work, you're welcome to. P of A plus H. Alright, so I've got negative. Let's see how quickly we can do this. You have the advantage of being able to pause, which is nice, so I can just kind of cruise through this. Hopefully not making any mistakes. Keep an eye on me. So I plugged in my A plus H, and then I foiled and combined like terms, and now I've got this additional little step here where I have to distribute this minus sign into what I have foiled and combined like terms, so make sure you do that. Alright, and then I'll just jot down P of A. And then I'm ready to plug these expressions into my difference quotient. And I've got a photocopier running in the background if you can't hear. It's a good indicator that I'm actually in my office. It's not just a stage that looks like my office. I don't want an equal sign there. First I have to write down the limit as h goes to 0. And then we've got our difference quotient here. The biggest fraction maybe that we ever work with. And I've got negative a squared minus 2ah minus h squared, etc. And my eye is always going up and checking to make sure that I'm copying each one of these terms down correctly and got the signs correct on all of them. So I'm in good shape there. And then I have to extend this line a little bit because now we need to subtract. And then in parentheses, negative a squared plus 10a minus 21. Goodness. Alright, let's start canceling some stuff out. First, we're subtracting a negative a squared. So that negative a squared turns into a plus a squared, which will cancel out with this minus a squared. And we're subtracting a positive 10a, which will cancel out with this positive 10a. And we're subtracting a negative 21, which is like adding 21, which would cancel out this subtracting of 21. Alright, we knocked out all three terms from the second part of our difference quotient with three terms from the earlier part of our difference quotient. Then let's start getting rid of some h's. H from the denominator is going to knock out an h there, and one of these factors of h, and this h, and let's write down what we have left. It's the limit as h approaches 0 of, it's not a fraction anymore, negative 2a minus h plus 10. And I'm looking to make sure that I like that, and I do. Great, now let's apply the limit. So we'll do direct substitution, getting that h value of 0 in there. So that's equal to negative 2a. I don't want to write it there. I'm going to write it on the next line down. So this statement's equal to this statement, which is equal to this statement, which says negative 2a plus 10. And then we'll plug in our given a value, which is an x value of 3 up there at the top of your screen. So that 3 is going to come down here. A equals positive 3. So we've got negative 2 times positive 3 plus 10, which is negative 6 plus 10, which equals positive 4. So the marginal profit at x equals 3 is 4. There's a rhythm to these, and it's worth practicing enough of them that you can do them quickly and accurately. Make sure that you're moving at a speed that is going to ensure your accuracy, because There are a lot of opportunities to make little mistakes, and we don't want to make mistakes. You don't want to do these problems any more than you have to. So let's slow down just a little bit, pick a good steady speed that allows you to get these problems correct the first time, and I will see you next time. Thanks.